Hearing aids are smaller and more powerful than ever. Researchers seek to improve the quality of sounds by amplifying the sound signal while reducing the surrounding background noise. A team from the University of Texas, Austin, designed a device that mimics the hearing mechanism of a parasitic fly called Ormia orchacea. This fly determines the location of its prey, which is a cricket, based on its chirp. The catch is that its hearing organ spans only 1.5 millimeters, which is 10 times smaller than the wavelength of the cricket's chirp. To understand the problem, in larger animals such as humans, the brain is able to determine the source of sound based on a split-second delay between its being detected by the left and right ears. The two sound features are called interaural time difference and the interaural level difference. The interaural time difference is in the time it takes sounds to reach each ear, while the interaural level difference is the difference in sound intensity measured between both ears. On the other hand, the fly is so small that sound waves are longer than its body, wherein sounds register on both sides of their body almost simultaneously, such that they can't tell the difference in arrival time. However, the fly possesses a minuscule seesaw-like structure where any movements on the structure amplified vibration on one side drives the other in the opposite direction, thus letting the fly know the sound's direction of travel. The fly uses two modes of vibration, which serve to amplify interaural and level differences. These are the bending and rocking actions, where the net effect is to increase the asymmetry of the membrane vibration. Other teams have already tried to build hearing devices that emulate the fly's superhearing, ever since the fly's hearing mechanism was understood decades ago. The difference now is that this team is the first to use piezoelectric materials, which convert mechanical pressure into electrical signals, which allow the device to work with little pressure, as battery is the primary cause for the bulky structure of hearing aids. They use the flexible silicon beam, suspended by two pivots, and integrated piezoelectrical materials in 4 sensing ports, allowing the device to simultaneously measure both the amount and direction of the sound-induced vibrations. The device is 2 meters, which is near the size of the fly's hearing organ. Currently, the team has published a paper on this device in Applied Physics Letters. It is not yet available commercially, but is targeted mainly to improve hearing aids, especially those that use directional microphones, which allows you to hear sounds directly in front of you more clearly than to the sides, so you can focus on conversations without worrying much about background noise. This technology is also intended to be used in military and defense applications, like in dark environments where visual cues are absent. This kind of application can be hinted as this research is funded by the Defense Advanced Research Projects Agency. In the Philippines, the prevalence of hearing disability is 8.8% of the population. Further, hearing impairment, including mild forms of hearing loss, was at 28%. Also, Philippines has the smallest ear and hearing specialist population in Southeast Asia. With this technology of hypersensitive hearing device, minus the bulk and cost of its structure, many Filipinos would benefit from it, and it could be modified for applications that could amplify sounds for the deaf. This technology could also be used for surveillance operations, monitoring of disaster operations, and also military operations that need sensitive sonic application. There is a patent by Ronald Miles, one of the first researchers that discovered the hearing mechanism of the fly, which uses optical sensing with the use of diffraction grating in place of the piezoelectric materials to transmit electrical signals from a rotating diaphragm that responds to pressure gradient.